Okay, there we go. Hey, Sebastian, can you hear me okay? Are you there, Sebastian?
Yeah, I'm here. Sorry.
Okay, yeah, no worries. Okay. All right, guys. So we've got four sections left. 17, 4, 5, 6, 7, 8. So I guess we got five sections left. Um, the last part of this class, basically, we're going to be extending the fundamental theorem of calculus part two. This is that theorem that we've been using throughout. You guys use it almost every day. It's this guy right here. Remember this guy? That's the fundamental theorem of calculus part two. It's the most important theorem. If there's one thing that you learn from calculus, it should be this, because basically what it allows you to do is to turn off my alarm here, is to evaluate integrals. Sorry. Uh, to evaluate single integrals, real quickly, you don't have to use those rectangles that we did in Calc 1, if you remember that. It takes a long time to do those. Dogs. Okay. Give me just a second here. I'm sorry. Hey, no. Stop. I'm in class right now. Okay, thanks. Alrighty. Okay, so we're basically going to extend this theorem again. We've actually already done it once, so let me kind of recap on that. So here's the fundamental theorem of calculus, part two. Couple of things I want you to notice here. One of them is that the integration is occurring over a region A, B, and R. That's an interval. So we could picture this region that we're integrating over. It looks like this, right? That's what we did in Calc 1. We integrated over an interval or a region in R1. And so the big idea here is that what the fundamental theorem of calculus does is it relates the integral of f prime over this interval, this one-dimensional region, to the values of f, which is the antiderivative of f prime, right, at the endpoints. So in other words, we're able to find this integral, which is occurring over this entire region, by simply evaluating f at just the endpoints. We could ignore everything inside. So it's a very powerful theorem because it basically allows you to ignore everything inside as long as you can find f. All right. Okay, so what are the endpoints? How as dogs? What are the endpoints? Well, the endpoints are basically the boundary of this interval. That would be the A and the B. So they're on the boundary, the ends. Okay, so the first extension that we looked at, we actually saw in section 17.2, the fundamental theorem for line integrals. And that was our first experience with an extension of the FTC2. This is what the fundamental theorem of line integrals says. I'm sorry, guys. Give me a second. Hey, guys, come here. Come. Come on. Come on. Come on. Over here. Over here. Come on. Come on. They're over here. Over here. Oh, over here. Come on. Let's go. Come on. Hey, Dad. I'm sorry. I'm in class right now. Can you grab the dogs and put them in my other room? Thanks. Thanks. Sorry. Sorry, I didn't say hi. I'll be on the lookout. Okay. Sorry about timing, guys. Okay. All right. So this is our extension. Now, the first thing you want to ask is, where does the integration occur? Well, up here, the integration occurred on a one-dimensional region in R. But over here, the integration is occurring over a curve, a parametrized curve in R2. Or you can also do it in R3. But let's keep it simple. Let's just look at it in R2. So what does the theorem say? Well, it says that if you want to evaluate this line integral over this entire curve from A to B, as long as you can find phi, which is sort of like the antiderivative of the gradient of phi, it's a higher dimensional version. Remember, the gradient kind of acts like a derivative in a sense. then you can evaluate the line integral by simply evaluating phi at the endpoints and subtracting. It's very similar to what we did with the fundamental theorem of calculus part 2. Okay, so what does it do? It relates the integral of the gradient of phi over a piecewise smooth curve oriented in R2 or R3 to the values of phi at the endpoints. And by the way, the endpoints would be the boundary of the curve, right? If this is your curve, then that would be a boundary point, and that would be a boundary point. Okay, so that was our first experience with an extension of the FTC2. Well, it turns out there's more extensions. In this section, we're going to study Green's theorem, which is also an extension of the FTC2. It's kind of another higher dimensional extension. There's two forms. One's called the circulation form, and the other one's called the flux form. And this is the notation that I use: Green's theorem, circulation form, and Green's theorem, flux form. Okay, so what's different about this extension? Well, we'll get to the theorem in just a minute, but the fundamental difference is that instead of integrating over a line in or an interval in R1 or a curve in R2, we're going to integrate over a region in R2. Okay, so this is what our region is going to look like when we finally get to the theorem. So the region R is this kind of region in this light blue color. So what you want to notice is that the region is connected and simply connected. And then also we have to put a requirement on the boundary of the region. The boundary of the region is a closed curve which wraps around the edge of this thing. And the curve has to be simple, piecewise smooth. And it has to be, this is important, it has to be oriented in the counterclockwise direction when it's viewed from above. So if you look at the curve, the boundary of this region R, if you look at it, you can see that it's rotating in this counterclockwise direction. That's important. It has to be oriented in that direction. The reason for that is because of this vector n. You know, t always points in the direction of movement, so there's no problem with t. We've talked about t since the first chapter, back when we started this class. But we're also going to need a normal vector. And it turns out there's actually two normal vectors. There's one that points inward, and there's one that points outward. And we have to make sure that we always use the same one. And so the way we do that is we make sure to orient in the counterclockwise direction. And the normal vector will always point to our right. So if we're driving in a car, walking along this curve, the tangent vector points in the direction of motion, while the normal vector is uniquely defined to be the one that points in the outward direction. So it's out of the region R. Is that okay so far, guys? Any questions so far? Okay, I'll assume you guys are doing it. All right, thanks for the thumbs up, Damien. All right, okay, so we're going to introduce Green's theorem, but just want to point out that this is the region we're integrating over, just like this was the region we integrated over for the fundamental theorem of line integrals, and this was the region we integrated over for the fundamental theorem of calculus part 2. So we're just integrating over different types of regions. By the way, in the last two sections, 17 and 17.7 and 17.8, we're going to integrate over regions in R3. So this is a region in R2. So you can kind of imagine that if you get good at this, it'll help you with those last two sections. Okay. All right. So for all of the problems that we deal with in this section, you can assume that your regions look like this. Okay. So the region R will look like so, and the boundary curve will be wrapped in this kind of counterclockwise direction. All right, so before we get to Green's theorem, we need to know what curl is. So the big picture is that curl is basically a measure of the rotation of a vector field. The formula for curl, if it's a two-dimensional vector field, is given like so. This is the notation we use, curl of f, but this is what it is. It's the partial of g with respect to x minus the partial of f with respect to y. And you can write it, usually I'll write it like this. More simply, it means the same thing, right? Just different notation for the same thing. So what is this thing? Well, it turns out that the combined effect of subtracting gx minus fy gives us basically the net circulation across a tiny circle enclosing any point in our vector field. I know this is a lot. However, when I show you the picture, I think it'll clear up some of your questions. Okay, so let's say that we got a vector field F. Okay, so that's everything in red there. And then I'm going to place one of those regions R somewhere in the vector field like so. And then I got to make sure that its boundary is oriented in the counterclockwise direction. So this is the setup. It looks like this. Okay, so do you guys remember what it means, what the circulation of F on C means? This is a notation we use for the circulation. Sometimes I would use a T. You could write it this way too. It means the same thing. Do you remember what this means? Like for example, on this problem, would you say that there's positive circulation on C or negative circulation on C or no circulation?
Positive.
Yeah, it's positive, and the reason why is because if you walk along the circle C in the forward direction, all you want to do is ask yourself, is the vector field agreeing with your movement or disagreeing with your movement? And in this case, it's always agreeing with the movement. So, the net result is we're definitely going to have positive circulation here. You remember that? We studied that in, I think it was 17.2. Okay. All right. So we know the circulation. We know that this right here is positive. Now, I want you to imagine that this vector field that I've drawn in red models fluid flow. Okay, so it's kind of like a toilet flow or maybe water in a swirling eddy, just kind of going around in circles. Now, one of the things you might ask is, okay, so the circulation on C is positive. Does that have anything to do with the rotational effect of the vector field inside of the circle? And it certainly seems like it does. It seems like there's something happening in here that's causing the circulation on the boundary of R or C. All right, so the way we can kind of visualize this is imagine placing a paddle wheel, somewhere in R like so. So now you've got this water that's kind of pushing on the paddle wheel, and the paddle wheel is either going to turn, it's got a direction. It's either going to turn in the counterclockwise direction like it is right now, or, if the water's pushing harder the other way, then it would rotate in the clockwise direction. And then also it's going to rotate with a particular strength, right? Or rate of rotation. If it rotates really fast, it means it's, the water's causing it to turn real fast at that point. So what does this have to do with the curl? Well, this is basically a visual representation of the curl. And you can find the curl at any point. It just so happens the curl is the same everywhere inside this vector field. So would you say that this curl is counterclockwise or clockwise rotation?
Counterclockwise.
Yeah, it's counterclockwise, right? So now we're interested inside of R right there. Okay, so let's look. All right, well, if the curl of F is positive, if you evaluate this guy and you plug in whatever the coordinates of that point are, let's say like 1, 1, and you get out a positive number, that's going to tell you that the paddle wheel is going to rotate in the counterclockwise direction. So that's important. Remember, for a curl, counterclockwise means positive. Okay. Now, if you plug in another point and the curl is negative, what would happen is your paddle wheel would rotate in the other direction. Now, as far as the strength or the rate of rotation, how fast it's turning, you can also get that from the curl. All you got to do is find the magnitude of that guy, and it's just a real number, right? You could find its magnitude quite easily, and that would tell you how fast it's rotating, basically. So let me give you a more general picture. Where did they go? All right, I lost my things. Give me just a second. I got to drag them in. All right, so let's look at a more general case. All right, so first I'm going to lay out the vector field. Okay, there's your vector field. And what I'd like to do is find the curl at a specific point in the vector field. So let's go up, maybe, let's go to right here, right there. Now, if you were to place a paddle wheel right there, would you say that the paddle wheel is going to rotate in the counterclockwise direction or the clockwise direction? Remember, this is water flow, right?
Clockwise.
Oh, okay.
No, that's okay. Well, so what you want to do is kind of ask yourself, okay, so we've got this water that's pushing it in the clockwise direction up top. And then down below, we've got water that's moving faster, that's pushing it in the counterclockwise direction, right? So in this particular case, the paddle wheel is going to rotate in the counterclockwise direction. See, these vectors are longer down here, so they're pushing it faster, and they're pushing counterclockwise. And these ones up here are pushing clockwise, and they're shorter. So, and also there's this kind of, you can see the vectors are kind of turning in this direction up here. So it seems, does that make sense why this would rotate in the counterclockwise direction there? Okay, okay, all right, good. All right, so and we could do this at every point, but here's the idea. If you were to calculate the curl, this is something you guys can do. Take the vector field, find gx, find fy, subtract them, and then plug in the coordinates of this point. Let's say this is over at -1, +1, and you plugged in the coordinates into the curl. What would end up happening is you'd get a positive number out. Now, you'd get a negative for the fy and a positive for the gx, but a positive minus a negative, a double negative is a positive. You end up getting a positive curl there. So that's why you have counterclockwise rotation. And now you can do this at any point. You could go over here and you'll see that, you know, where gx and fy lie at that particular coordinate. You could go over here, anywhere you want. So let's see if we could find one. This is counterclockwise. Let's try and find a point where we have negative curl or clockwise rotation. So let me move around. Okay, there we go. So over here, what's happening is your paddle wheel is rotating in the clockwise direction. Now, intuitively speaking, can you kind of see why that would happen? Like, ignore the gx and fy, just look at the red vectors. Does it make sense that if you put a paddle wheel there, it would rotate in this clockwise direction as opposed to counterclockwise? Okay. All right, good. Yeah. Look, the vectors are kind of shorter on this side and longer on this side. So that's going to push it in the clockwise orientation. There's also kind of, you can see the vectors are changing directions and they're kind of doing this. So yeah, so remember, if the curl is negative, which in this case it is, your vector field will have negative curl there. And if the curl is positive, then you'll have counterclockwise rotation there. Is that okay? Do you guys have any questions on that? it's just a way to have some intuition as far as what the curl is. But the formula is right here. You're just going to use the formula. If you're interested in knowing, you know, what's happening under the hood with GX and FY, you know, I'll kind of explain. I'll do one of them. I'll do GX. You know, if I take the vector field and then I just take a cross section in the X direction, like so, the GX at this point is essentially the rate of change of G in the X direction. And I am moving in the X direction here. So remember, G is the second component of the vector field, which is the vertical component. So what you want to do is ask yourself, as you move from left to right over this point, is the vertical component getting larger or smaller? And in this case, the vertical component, the length of that green line, is getting longer. That's why GX would be positive there. And I'll do FY too. Now FY, this is a cut in the Y direction. So this is the Y direction. So if you move in the positive Y direction across this point, what you want to do is ask yourself whether the F component of the vector field, which is the first component, or the X component, you could say, the first component, whether it's getting longer or shorter as we move in the positive Y direction. And it doesn't seem to be moving too much right there. So you might say FY is 0. But you could do this at any point. That's essentially what's happening, why those values FY and GX have a particular sign. Okay, so that's what's happening under the hood, but you don't need to know that. You know, we just need to know the curl. All right. Okay, so now we're ready for the first form of Green's theorem. All right, here we go. Now, this is an extension of the FTC2, and there's two forms, the circulation form and the flux form, and they look very similar. This is the circulation form. Now, the setup is the same, so you can kind of ignore this because we already know that C is a simple closed piecewise smooth curve oriented counterclockwise, enclosing a connected, simply connected region R. So we already know what the picture looks like. It looks like this, oriented counterclockwise. So what does Green's theorem say? Well, it says if you have a two-dimensional vector field where F and G have continuous first partials in R, then let's see. Well, I wrote, okay. Then the circulation on the boundary of R is equal to the double integral of the curl on the region inside. All right, give me just a second here. Okay, all right. Sorry, I got some people here. Okay. All right, so what is this theorem actually saying? Well, it's actually saying the same thing as the FTC2. If you think about what it's doing, it's relating the curl of every point inside R, the integral of the curl, to the circulation on the boundary of R. So what's the boundary of R here? What am I referring to when I say the boundary of R? What do you guys think? What do I mean when I say the boundary? What am I referring to?
The domain, like the XY coordinates.
Well, the boundary of R, if you think about this light blue region, would be the curve C, right? That's this guy?
Yeah.
Okay. Now remember up here when we did this introduction, we talked about the boundary of the interval A to B was just the points A and B. And the boundary of our curve up here would be the points A and B. Well, analogously, now that we've moved to a region in 2 dimensions, When we talk about the boundary of R, we're referring to the curve, the closed curve that encapsulates R. So if you think about what this is, hold on guys, I'm sorry, I gotta move. I can't hear. Sorry guys.
Yeah.
I'm gonna move in your room backstairs. All right. All right, sorry for the noise, guys. All right, okay, so it does the same thing. Basically, it says that if we integrate the curl at every point inside, you could evaluate that integral fine. It's just a double integral, but if we wanted to, we could do the same thing by basically finding the circulation on the boundary. Okay, it's a direct extension of the FTC2. It's basically saying the same thing that we said with the fundamental theorem of line integrals. In a sense, what it's saying is that if you add up, you guys remember what integral means, right? It means you add up all the little curls. That's what this means. So we're going to add up all the little curls at every point inside. And when we do that, the result is going to be the circulation on the boundary. Okay, we know how to do both of these integrals. We've done line integrals, we've done double integrals. What the theorem is saying is it's relating the two. It's saying that these are actually the same thing. So let me give you some intuition on what's happening. So let's take that same example we were looking at before. For this example, you told me the circulation was positive, right? That would be the left-hand side. So the circulation on the curve C is positive here. Well, what Green's theorem says, it says if you add up all of the little curls at every point inside, all the tiny little rotations at every point inside the region R, then you should get the same thing. You will get the same thing. Okay, so we know how to find the curl at a point. You just stick a paddle wheel down there or calculate the curl, right? But let's say we wanted to do this at all points within R. So let's do multiple points, right? So, and then we'd want to make it an infinite number of points in there. But look what's happening. Let me zoom out a little bit. You know, when you rotate in the counterclockwise direction for all of these, what's going to happen is there's going to be cancellation. If you were to calculate these little mini circulations on each one of these guys, they're going to cancel here because do you see they're rubbing against each other? One's rubbing down and one's rubbing up. They're canceling basically everywhere. And even as I increase the number of points visually, you can see what's happening is everything inside is canceling because they're rotating against each other in opposite directions. And as we increase the number of points, you can still see that everything in the middle is canceling. So then you ask yourself, well, what's left if everything in the middle is canceling? Well, the only thing that's not canceling is everything on the boundary because there's nothing outside to cancel with. So that's why if you add up all of the curls, everything in the middle cancels except for what's left on the edge. And what's left on the edge is the circulation. Does that make sense? Does that give you a general idea of what the theorem is trying to say? Okay, how about everybody else? Zoe, Sophia, Damien, Omar, are you okay? Okay. It's a more complicated theorem, but the idea isn't too bad. So that's the Green's theorem circulation form. All right, so let's go ahead and use it. Do I have one? Yeah, let's skip down to this one. Yeah, let's skip down to this one. We'll come back to, I probably should have done this first. Let me move this. All right, let's skip over this irrotational stuff. Let's go right to an example. Actually, I'll just do this. I'll move this up here. There we go. All right, so let's see. So let's say we have this vector field. That's a rotational vector field, and then we've got a unit circle oriented in the counterclockwise direction. Looks like I lost it. Where did I put it? Oh, I lost it. Let me see if I can grab it again. Oh no, I lost it. Darn it. Okay. Okay. There, I'll move. Okay. Okay. All right. All right. Where is it? Oh, darn, I lost it. Oh, here it is. Okay. Solution. Yep, there it is. Okay. All right. Do you guys remember doing this one? We actually did. This is the same example we're looking at above. Do you remember we calculated the circulation? It's positive, and we found that the circulation was 2 pi. Does that sound familiar? Not sure. Okay. Well, we did that in 17.2. We know it's positive, right? But we actually ran the calculation. It was just a line integral, so you might want to review that. So what we're going to do is we're going to confirm Green's theorem using this as an example. So here we go. So on the right side of Green's theorem, where is it? Here we go. We've already done this side. We showed that it was 2 pi. So we're going to do the right side and show that we also get 2 pi. Okay, so let's do the right side. Well, in order to do the right side, we're going to have to find the curl. So here's the curl, right? It's gx minus fy. So let's find gx minus fy. Okay, so remember the first component is your f component, and the second component is your g component. Okay, so if we want gx, we're going to take the partial derivative of the, sorry, I did this backwards. Oh no, did I write this backwards? FG. I did write this backwards. It was, the vector field was negative yx. Give me just a second here. It looks like I got something mixed up. Gx minus fy. Okay, this should have been negative y. That's x, is that right? That's the partial of g with respect to x minus the partial of f with respect to y. There we go. Okay, I just had it backwards. All right, so we evaluate the curl. In any case, we end up getting 2 for the curl. Okay, so now we're going to evaluate the right side of Green's theorem. So the right side of Green's theorem is right there. So we simply just plug a 2 in, and then we evaluate the double integral using everything we know about double integrals. By the way, this is a very easy one because the region of integration here is a unit circle, and we already know the area of a unit circle. It's just pi. So we don't even need to evaluate the double integral. We can just shortcut it. We know the area of R is just pi. Okay, so what does that mean? That means we get 2 pi if we use the right side of Green's theorem or the left side of Green's theorem. In other words, the circulation on the boundary is the same as the accumulated curl at every point inside. Is that okay? Hopefully it's okay. All right. Do you guys have any questions on that one? Can you guys still hear me?
I don't know why it wasn't letting me unmute. The partial of G to X wouldn't like because there's no X component in G in the vector of field of F.
Let's see. Oh, you're right. Okay. No, I
So
did.
when you switched it, I think it was best the way it was.
Yeah, you're right. I think I did mess that up. Okay. What did I switch?
So it was negative Y and then X. Yeah,
Okay.
I think. Yeah.
So the partial of G, hold on a second. Partial of G with respect to X. So this would be G. Okay, something's off here though. FG, so that would be, oh, no, I just wrote these in backwards. Okay. There we go. My bad. Thanks for catching that. Does that work?
Yeah, better.
Okay. Yeah, so this is F and that's G. Yeah, okay, perfect. So this was fine. I just wrote in the wrong functions there. Okay. All right. So thank you for clearing that up. That helps me a lot. Sorry guys, I'm got a bunch of stuff going on here. I'm trying to keep my head straight. All right, I'll have to clean this up afterwards. Okay, so that's an example. All right, what's next? Well, we're dealing with curl. So let's say you have a vector field that has no curl at all. That is at every point in the vector field, let's say the curl of F is equal to 0. Essentially what that would mean is if you took a paddle wheel and you placed it anywhere in the vector field, it would never rotate at all. So when that happens, you say that the vector field is irrotational, which kind of makes sense, right? There's no rotation at all. All right. Well, if a vector field is irrotational, what would Green's theorem say about the circulation? Well, this is Green's theorem, right? So if the curl is 0 everywhere, no matter what the region R is, then what it says is that the circulation on any closed curve in any closed curve that goes through the vector field, the circulation will always be 0. So that means that irrotational vector fields, the circulation is 0 on every closed curve. Now we can back this up a little bit. We know what a conservative vector field is. If you have a conservative vector field, it means that Gx equals Fy. We learned this in 17.2. Maybe it was 17.3. But these are those special vector fields. But if Gx equals Fy, that would imply that Gx minus Fy equals 0. And if Gx minus Fy equals 0, that's the curl. So that means that all conservative vector fields are irrotational. So that's a way to kind of classify these things. If you see a vector field that's got no rotation at all, that means that the vector field is conservative. Okay, and in a conservative vector field, what that means is that the circulation on any closed curve is 0. So in other words, if F is conservative, then the curl of F is 0. If the curl of F is 0, then F is conservative. All right. All right, there's another kind of trick you can use with Green's theorem. It's a way to calculate the area of a region. Here's the theorem. It basically says that if you have the conditions of Green's theorem, right, appropriate region R and appropriate counterclockwise rotation along its boundary, then you can calculate the area of the region R by simply evaluating either one of these line integrals, these circulation integrals, I should say. By the way, you can combine these, you can add them up and divide by 2, and it gives you another way. So you could do it this way too. So you might ask, well, where does this come from? Well, here's the idea. Let's say that I give you this particular vector field. So this is special. It's specially constructed. Do you notice that GX is 1? You guys follow that? This is F and that's G, right? So GX is 1. And then can you see that FY is 0? Okay. So by Green's theorem circulation form, what we have is that the circulation on the boundary is equal to the sum of the curls at every point inside. And we know that gx minus fy for this particular vector field is 1 minus 0. So basically, we're just integrating the one function over R. And if you remember back from our study in double integrals, the integral of the one function is the area of R. Okay? All right, so where does all this stuff come from? Well, this is just alternative notation for the same thing. If you remember, f dot t ds can be expressed this way. F is this vector field 0x. And dr, well, that's just the differential of the curve. So whatever that is, dx, dy, of course, you'd have to find dx and dy, but we'll leave it in this form for the notation. And when you dot these together, you end up getting x dy. So what the theorem is saying is that the circulation along the boundary of C, which reduces to this notation for this vector field, gives you the area of R. And the same thing happens if you choose this vector field. If you find gx and fy, and then you evaluate the circulation on any closed curve C, you don't actually get the area, you get the negative of the area. So what that means is that the area of R equals the negative of the circulation. So in other words, these guys are formulas for finding the area of a region R simply by evaluating a circulation integral. Actually, they're still in use today, just not as much, but back when my parents were probably learning calculus, there was a popular engineering tool called a planimeter, and it wasn't electronic like this one. But what this is it's a machine that uses Green's theorem to calculate the area of a region. So if you look at this region, that's a simply connected region. And if you take this little magnifying glass, see that little dot, and you follow the dot in the counterclockwise direction along the edge of this thing uses Green's theorem, basically uses these guys to find the area of the region. So if you're interested, you could watch that video and see how it's done. But they don't really use these as much today because we just use software, right? But the idea is the same.
When the Davises booked their Verbo vacation.
All right, so let's use it. Let's use it to find the area of an ellipse. So we've got an ellipse, and let's use the third formula, this one right here. It's just a combination of these two. All right, here we go. All right, so first we're going to need to parameterize the curve. All right, so how do we parameterize a curve? Well, if it was a circle, it would just be cosine t sine t, right? But the fact that it's stretched in the x direction by a factor of a and the y direction by a factor of b, creating this ellipse, means you just put an a in front of each, an a in front of the first component and a b in front of the second component. And then we let t range from 0 to 2 pi. Is that fair? Does that make sense? Why that would be a parameterization of an ellipse rotated counterclockwise? The A and the B are just stretching things out a little bit, right? Okay. Any other questions? Sophia, Zoe, Damien, Omar? You're okay? Okay. All right, good. All right. Okay, so now that we've got the parameterization, let's go ahead and use that formula. We're using this one. So in order to use it, we're going to need to find dy and dx. And the dy and dx basically come from your curve. So in the x and the y, well, that's from your vector field. So we just replace x with a cosine t. You need to express it on the curve. And the dy becomes b sine t. Dt, by the way. And the y becomes b sine t. And the dx becomes a cosine t dt. And then at this point, all you're going to do is simplify. So we'll pull out all the dt's. We're treating them like differentials. And we'll pull out the a and the b, and the cosine squared plus sine squared reduces down to a 1. So then you're just integrating this constant ab. So we can pull the constant out, and then we're just integrating the one function from 0 to 2 pi, which is 2 pi. So when we run the calculation, we get pi times ab. Okay, so that's the area of that region R, of the region inside this ellipse. By the way, that's the same formula that you discussed back in geometry. Let's say A and B are the same. Then it would be a circle, right? If A and B were the same number. Like if that was an A as well. Well, in other words, replace that B with an A, and then you have the formula for area of a circle of radius A, pi a squared. Okay, that okay? Any questions on this one? Okay. All right, let's keep going. Okay, so we've conquered, let's see. Let me wrap this up in here. I'll have to fix this. Hold on, I'm gonna move rooms. Give me a second here. All right, one more time. All righty. Let's see, curl, calculating area. Okay, so now let's move on to divergence. All right, so if you got curl down, divergence is like the analog of that. So if you remember, curl measures rotation. Divergence measures dilation. The way to think of dilation is it's expansion or contraction. Okay, so like when your eyes dilate, if you ever get pulled over and they shine the flashlight into your eyes and they see whether your eyes are opening or getting larger, your pupils are getting larger or getting smaller. We call that dilation. So a two-dimensional divergence of a vector field is given by, this is the shorthand notation, div f. And this is the divergence. And you could write this in shorthand notation as fx plus gy. So what is this? Well, it turns out this combined effect of adding fx and gy at a point, it gives us the net flux across a tiny little circle enclosing a point in the vector field. Okay, so here's the big idea, and we'll use a similar vector field to the one we looked at above, only this one will be radial. So let's suppose we got a vector field. It's the same thing. It's connected, simply connected region R, and then the boundary is a simple piecewise smooth curve oriented in the counterclockwise direction. Do you guys remember this? That's the flux, right? The flux on the curve C. So in this particular case, is it clear that the flux is positive? This is something we learned back in section 17.2. So I'm just looking at the curve, not the region, right? What's the flux on the curve C? Is it positive or negative, and why?
Is it positive because the vector field is pointing out?
Yeah, it is. So it's because it's pointing outward. So flux is basically a measure of how much the vector field passes through at kind of a right angle or passes through the curve. And we define a positive flux as passing through in the outward direction. So it looks like as I move around this vector field in this counterclockwise direction, the vector field is always pointing in the outward direction. So I'm only seeing positive contributions to the flux. So if I add up all of those positive contributions, clearly the flux is still going to be positive. Okay. All right. Now the divergence is kind of like a mini version of that. It's happening at points instead of on a circle. Oh, give me a second here. Thank you. All right. So, all right. All right. So what are we talking about? Well, okay. So here's a way to visualize divergence. I want you to think of, again, the vector field is modeling like fluid flow, but it's hard to imagine what this is doing as far as fluid, because everything's expanding from the center. Well, imagine that you're looking down at the floor of a bathtub, or maybe let's say a bathtub. If you look down on the floor and you turn on the water on the faucet there, the water is going to hit the floor and it's going to expand outward. Okay, so that's a way to visualize this as water flow. You've got basically the source of water that's hitting the floor and expanding outward. So let's look at the dilation or the divergence at every point. So the way to visualize divergence is basically using like a pulsating disk. Now the disk is either going to pulsate in the outward direction, indicating an outward dilation, or it's going to pulsate in the inward direction, indicating an inward dilation. So it turns out that when the divergence is positive, that means outward dilation. And if it's negative, it's going to be inward dilation. So if the divergence is positive, it's outward; negative, it's inward. And the rate at which it's dilating, right now it's dilating maybe about once every second or so, something like so. But it might dilate faster or slower, but we can get the rate by finding the magnitude of the divergence. Okay, so one thing you might note is it seems like, we already found that the flux on the boundary, flux on C, was positive. So you might ask the question, does that have anything to do with the divergence at all of these points inside? And it seems like it does. It seems like if we added up all these little divergences inside, we would get the flux on C. And that's exactly what we're going to show. And that's exactly what Green's theorem says. So here's Green's theorem, and this is the flux form. So this is the flux on the boundary. That's the same flux that we calculated in 17.2. And what this is it's the sum of all of the divergences. It's the accumulated sum of all these divergences. Okay, remember your region looks like this. Instead of working with a tangent vector, you're working with this specific normal vector oriented in the outward direction. Okay, so let's see if we can get some intuition as far as why adding up all of these guys, all of the little tiny rotations, all of the little divs, gives us the flux just on the boundary of the region, or the boundary curve C. Well, if we add up all of the little divergences inside, what you'll notice is that if you take two that are right next to each other, like this one and this one is expanding outward, and this one is expanding outward. So there's a cancellation between these two. And that's actually true between any two pairs. Here, everything in the middle is canceling. And even if we make our model look a little better with more of these, you can see that everything in the middle is canceling out. And if we were to keep on kind of expanding to infinity, what you'd notice is that everything inside the region is canceling. The only thing that's not canceling, the only thing left would be everything on the boundary. And if we're talking about expansion on the boundary, that is the circulation on the the flux on the boundary, right? That's what this is. That's the flux on the boundary. Okay, so it's the same idea that I showed you above. Everything in the middle cancels. The only thing you're left with is what's on the boundary. All right, does that idea make sense? It's analogous to what we talked about earlier with the Green's theorem circulation form. Okay.
Wait, actually, I have a question. Why does it cancel out again?
Well, okay. So the way to think of divergence is think of these as like, you might even think of them as like rectangles, like so. Let me see if I can draw on here. Can I draw? Yeah. So instead of a circle, let's do this. I'm going to draw this one and this one. Okay, so I'll draw a square like so. So let's see, they're expanding outward, right? So in all directions. So you can kind of think of this as like a mini flux where this is the curve. Remember, flux occurs on a curve. Now, if I've got one next to it, and it's also expanding outward, because they all have, in this particular case, they all have the same divergence. What ends up happening is right here, these guys cancel. Okay, now, so that means there's going to be cancellation here, 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 anywhere two of these things are next to each other, they're going to cancel. And in effect, as you draw more and more of these, it should be clear that everything in the middle cancels. The only thing that's left is all of these on the edge, because there's no circles on the outside to cancel with, if that makes sense. Does that help?
Yeah, that makes so much more sense. Thank you.
Okay, no problem. Okay, all right. So let's do one. Okay, so let's look at this one. This is the same one, right? This is a radial vector field. It's defined on this curve, on this region R, encapsulated by a unit circle C. And if you remember, we actually did this problem. We found that the flux on C, we found this flux was positive 2 pi. And what we're going to do is we're going to use the Green's theorem flux form to show that it's 2 pi using the right side of Green's theorem. And we'll get the same result because that's what Green's theorem says. Okay, so for the right side, we're going to need the divergence, right? That's the right side of Green's theorem. So we need fx and gy. We need to add them together. Okay, well, there's f and there's g. So we need fx plus gy. That's pretty easy. Fx would be 1 and gy would be 1. We add them together, which is 2. So the divergence at every point in this vector field is 2. Do you notice that the disk is expanding? It's dilating outward. That's why we got a positive 2 here. Oh, by the way, this vector field is pretty boring because there's no variable in there. That means that no matter where you are in the vector field, it's always expanding at the same rate. In general, that won't be true. In general, you'll have some variables in there, right? But we wanted to start off with a very simple example. The dilation here is always 2. Okay, so let's use Green's theorem. So Green's theorem says that if you want to calculate the flux on C, which we already found was 2 pi, we can instead do the right side of Green's theorem, which basically says we can add up all of the divergences at every point inside. So all of the divergences are 2, so we'll just integrate the 2 function over R, which is a unit circle of radius 1 And we already know that a unit circle of radius 1 has an area of 2 pi. I'm sorry, has an area of pi r squared, right? So 2 times pi would be pi. So we've just verified that the accumulated net divergence in R is the same as the flux on the boundary of R. Is that okay? Okay. Any questions so far? Okay. All right, let's try another. All right, this one looks super ugly, but actually it's just because it's expressed in a different form. So we're going to evaluate this this integral. Do you guys remember what that little circle means on the integral sign? What does that mean?
Is it circulation or no?
The circle means that the curve C is a closed curve. So this is a closed curve, right?
Yeah.
Okay. And this one right here, it's either circulation or flux. In this particular case, it's flux. Can you tell what gives that away?
No.
Okay, so it's the form. So we've got some function there, dy, minus some other function dx. So because it's in this form, this is a flux integral. What this is it's calculating the flux of the vector field on C. Now, if it was written in the form dx plus, and then there was a dy there, then it would be circulation on C. So it's just because of the form. All right, so let's see. So there's our inside or region R. This is a circle of radius 2 oriented counterclockwise. So yeah, so there it is. Yeah, remember this? I can't remember who was that, you, Omar? You remember this form? This is a differential form. They mean the same thing. So the fact that it's written in this order with the dy and then the minus and then the dx indicates that we're finding a flux integral. So all you have to do is identify the f and the g. We're going to use, we could evaluate the line integral and we could actually run the calculation, but I don't know. Let's use Green's theorem to evaluate the integral. Oh man, it's so loud here, guys. I'm sorry. Okay, so we got to find the divergence of f, right? So that's fx plus gy. So there's f. So there's fx and there's g. So there's gy. So there's fx plus gy. That's what we're going to use for our integral. All right, so there. Okay. So there's our double integral. Let's see. This thing is set up for polar, right? What makes this best to use for polar? Or why would we use polar here? What gives it away?
X squared plus y squared is R. R
Yeah,
squared.
Yeah, that's one reason. And the other reason is because your region R is circular, it's disk, and both of those are very good reasons to switch to polar, right? So we switch the thing to polar and then finish up and we get 96 pi. Now that's a positive number, right? Does that seem reasonable? Why we got a positive number for this flux? Remember, flux is the measurement of the let's see, measure of how much the vector field passes through the curve in the outward direction. Do you see that the contributions are all positive here as we go around. All these vectors are pointing outward, right? So, I mean, at least the sign is right. So that is technically correct, but I was more interested in just the sign. All right. So again, what Green's theorem is saying here is that if you want to find the flux on the boundary, it's sufficient to find the accumulation of the divergence at every point inside, and you'll get the same result. Is that all right? Okay. So you might ask, like, well, why would you use this theorem? Well, here's the reason why. It's the same thing with the circulation form. Let's say that I ask you to evaluate a flux, and let's say it's really hard to parameterize the curve, and maybe it's a bunch of pieces, and it's going to take you an hour to do. Well, if you can figure out what the region inside looks like, and you could find the divergence, which is generally pretty easy to find, all you have to do is do a double integral instead. So it allows you to bypass a lot of hard work. Or let's say that you have an integral of this form, and for some reason the integrand is really difficult. Well, if you can write it in the flux form, maybe it'd be much easier to do. It just depends. It's the same thing for the circulation form. By the way, that's why we use the fundamental theorem of calculus, right? Evaluating this is actually pretty hard. You got to use rectangles and stuff. I think using this is a lot easier. So we always use this to save time instead of doing all the rectangles. All right, so let's see, a couple more things. Oh, okay, so let's do circulation and flux on some more general regions. We've been doing these nicely shaped regions, but let's look at something else. Let's do a half annulus. Okay, so an annulus is it's like a disc, but it's missing the inside. So I think we had let's see, a solar eclipse late maybe a little while ago, and it was an annulus type. That's where you have the sun like so, and then you have the moon, which is almost blocking it, but the moon is too close to us, and it leaves this kind of ring around the moon, and that shape right there, this, oh, my dogs, that shape right there is an annulus. So this is a half annulus. So let's look at this vector field. Let's put it up. It looks something like that. This is a description for the half annulus. Hopefully you can see that's greater than the disk of radius 1. And I'm sorry, that's a greater than the circle of radius 1 and less than the circle of radius 9, which gives us this region. And the fact that y is greater than 0 gets us in the top half. We're going to find the circulation on C. Okay, so this is C. So you got to make sure to orient your curve in the counterclockwise direction. So hopefully you can see that our curve is oriented in this direction, counterclockwise as we move around it. Simply connected region R, simply connected region R, and then the curve is piecewise smooth, continuous, walking around in this counterclockwise direction. All right, so let's look at vector. I'm sorry, guys, give me just a second. I gotta trap this dog in a room. I can't think right now. Give me about 2 minutes here. Sorry. All right. Okay, let's try this again. All right, here we go. All right, so you tell me, we're gonna look at this intuitively first to see if we can take a guess at whether we think the circulation is positive or negative. So let's start with walking along the outside. Okay, so I'm gonna walk in the positive orientation. And remember, circulation, we're finding the agreement with the forward direction. So let me see if I can, let's use blue. All right, so I'm going to start here. Now, as I'm walking in this direction, do I have a positive contribution to the circulation or negative or no contribution? You tell me, positive, negative, or none? Right?
Positive?
Positive, still positive. And right about there, it goes 90 degrees, right? So I'd say there's no contribution right there. Is that fair to say?
Yes.
Okay, and I'm going to keep, remember, we're doing circulation, not flux. Now, if I keep moving, now we have a negative contribution to the circulation. Is that fair? Get lots of negative contribution here. Lots of negative even more negative contribution, negative contribution. Now, what about in this, as we walk along this edge? What's happening there?
No contribution?
No contribution. And now I'm going to keep walking along. So now what?
Now there's a little bit of more positive contribution.
Yeah, we have some positive contribution, but is it fair to say it's not very much because
Yeah.
the vectors are pretty short? Okay. And then I would say right about there, now we've got negative contribution again. But it's really short. It's not much negative, right? And then right here, I have zero contribution. So overall, on my entire trip along the thing, would you say the net contribution is positive or negative?
Negative.
I would say definitely negative. So I'm expecting the circulation for this vector field on C to be negative. Now, I can calculate it directly, or I could use Green's theorem. Green's theorem says that, instead of, I mean, this would kind of suck to do, right? Because you'd have to parameterize, if you wanted to use this, if you wanted to calculate circulation directly, you'd have to parameterize this curve. Then you'd have to parameterize this curve, and then that curve, and then this curve, and you'd have to do 4 line integrals. And that's a lot of work. If we use Green's theorem says that we can basically add up all of the curls at every point inside. We can find the net contribution of curls, add them up, and we'll get the same result. So in other words, let's see if we can get some intuition here. Would you say that is positive curl or a negative curl there?
Positive?
Yeah, it's rotating in the counterclockwise direction. So we got positive curl there. Positive curl there. Got even greater positive curl. Oh, wait a second. Yeah, positive curl there. But look what happens over here. We've got negative curl there. We've got even more negative curl there. Even greater, it's even more negative curl there. Lots and lots of negative curl. So I would say, just based on our intuition, it seems like most of the curl is negative inside this region. So, and this aligns with what we were talking about earlier with Green's theorem, right? I think if we add up all of those curls, we should get a negative result. So, let's see, let's evaluate the circulation. So you could use this form. I usually like to use this other form, but it doesn't really matter. They mean the same thing. And then this was the shorthand notation for the same thing. So you could write it this way, but we could just skip right down to here. So The circulation on C, which is the boundary of R, is given by integrating the circulation. I'm sorry, the curl. And the curl is 2x minus gy. So where's the curl come from? Well, the curl is, let's see, gx. I didn't write that in for some reason. Write it in here. It's gx minus fy. So all you got to do is find gx, find fy, plug them in. And now you've got this real basic double integral over the region R that looks like so. And by the way, this region R is built for polar. This is much better expressed in polar. You could do it in Cartesian, but it would be a real pain. So let's switch to polar. And the rest, I'll just assume you guys can get through on your own. But the important thing I wanted to point out is that we do get a negative result. So what we found is the flux, the circulation on the boundary of that region R, which is C, is negative 104/3. Is that okay? Go. All right. Now in the next example, let me just show you the picture first. We're going to be integrating this vector field. We're going to be finding the flux of that vector field. There it is. Over this region R given here. That's described here. Now, there's a problem with this region. It's not simply connected. In Green's theorem, you have to have a simply connected region. In other words, if you remember what simply connected means, it means that if you draw a closed curve in the region, in order to be simply connected, you have to be able to shrink that thing down to a point, and for that point to lie in the region, and we can't. This thing is blocking us. So Green's theorem doesn't apply, unfortunately. So we're kind of stuck. But there is a way to kind of fix this problem. What we're going to do is introduce a cut. We're going to take our region and we're going to add in a cut right here. Okay, if we add in this cut, then basically we've got this C. Hopefully you can see there's a C here. It's like the letter C, right? And there's a tiny little space right there. So now it becomes a simply connected region. And then we can orient the curve, in the forward direction, basically counterclockwise on the outside. On the inside, it'll be clockwise, but it's still oriented correctly. Okay. And if we do that, we should be able to find the outward flux using Green's theorem. So first, let's get some intuition here. Let me throw up the vector field. And let's put up this blue guy. And let's see, we're doing flux this time. So this one's going to be a little harder to get an intuition about, but let's try it. Okay, so I'm going to start here. I'm going to move in the forward direction. So would you say the flux is positive or negative on this first part?
Positive.
Positive. Still positive, right? Still positive. Probably maybe 0 right about there. What about over here? Is the flux positive or negative? Remember, we're talking about flux, which is a measure of how much the vector field passes through in the outward direction, out of the region, right? So is it positive contribution of flux or
Positive.
negative? Still positive, right? We have a lot of positive, a lot of positive contribution of flux over there. Positive, probably 0 right about there. Still positive. Still positive. Positive, maybe 0 right there. Positive, 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 and then 0. Now we're not done because we have to cut inside this region. Now, when I cut inside right here, remember I'm walking in the forward direction. So to my right would be this direction. It looks like it's 0. It looks like the contribution of flux would be 0 there, but maybe it's a little positive. Who knows exactly? But now let's move in this direction. Follow along our curve. And remember, to your right would be positive, right? If I look to my right, the vectors are pointing in the opposite direction. So we've got a negative contribution of flux as we move from here to here. Now, the vectors are pretty small though, so that's a pretty small contribution on the negative side of flux. And you'll notice as we move here, it looks like all of the flux is negative. All of the flux contributions are negative, except for maybe here and here where they zero out, but so we got some negative contribution to the flux. Not a lot though, the vectors are shorter. And then when we come back to where we started, we might have some contribution. But here's the thing, these two cancel each other out, the L1 and the L2, because they're just moving in opposite directions. So we actually don't have to worry about those. So overall, would you say that whatever we get for an answer here for the flux, would you say it should be positive or negative?
Positive.
Should be positive. We had so much positive flux contribution on the outer part of this thing. I think it far outweighed the negative contribution of the flux on the inward part, and these canceled anyway. Okay, so we're expecting a positive answer here. So yeah, Green's theorem doesn't apply, but we can make the cut. Let's see, here's your F, there's your Y. So if we wanted to use Green's theorem, the flux form, we would just simply add up all of the divergences at every point inside. So we'd find Fx, we'd find Fy, which are y squared and x squared respectively. This thing is definitely made for polar, so I would switch to polar and evaluate, and we get 15 pi over 2. So at least the sign is correct, right? We're definitely sure of that. Is that all right? Okay. All right. So those are the big two ideas that the big two things you're going to be working on in this section is using Green's theorem circulation form and the flux form. However, there's some other stuff that we'll just finish up with real quick because it's going to help you in the later sections. You know, there is an analog to a conservative vector field. It's kind of like it's the analog for flux integrals, basically. If you think about the circulation properties and the flux properties, the circulation properties kind of go along with conservative vector fields, and the flux properties go along with what we call source-free vector field. So what does it mean to be a source-free vector field? Well, it's the analog of a conservative vector field. If you remember, a conservative vector field is a vector field basically that has a potential function. A source-free vector field is the analog. It's basically a vector field for which there exists some function psi such that the partial of psi with respect to y is f, and the partial of psi with respect to x is negative g. And if that function psi exists, then we say the vector field is source-free. If you go back and look at what the definition of a conservative vector field is, it's the same thing. It's just that you have these different requirements on the partials. Okay, it's just the counter to a conservative vector field. It's on the other end. Instead of circulation, it's flux. All right, so what do we know about source-free vector fields? Well, if a vector field is source-free, it's pretty easy to show. It's analogous to what we showed with curl for conservative vector fields. With source-free vector fields, the divergence is 0. With conservative vector fields, the curl is 0. What does that mean? Well, that means by Green's theorem, if you evaluate flux for a source-free vector field, you'll always get 0, no matter what the curve is. Okay. So let's summarize kind of everything that we've been discussing so far. So these are the equivalent properties of a conservative vector field. All right. So by definition, a vector field is conservative if there exists a potential function phi. Do you remember this from section 17.3? Does that look familiar? Do you remember there's a test to determine whether a vector field is conservative? And then once you show it's conservative, you can find the potential function. You did that in 17.3. But if you think about what this means, this is what it means, right? It means that phi x equals f and phi y equals g. All right. So let's say you have a vector field is conservative. Well, if the vector field is conservative, that means that you have path independence. We talked about that in the last section. That means if you evaluate a line integral on a curve C, you can basically, this is the fundamental theorem for line integrals, says you can ignore everything that's happening on the curve except for the endpoints, and you can just evaluate phi of b minus phi of a. And if the vector field is conservative, it also means you have no rotation on the vector field. We just discussed that a second ago. And if there's no rotation on the vector field, then using Green's theorem, you can show that the circulation is always 0 on any closed curve, because that's just going to, when you write it as a double integral, you're just going to get a double integral of 0. So these are all equivalent properties of conservative vector fields. So if you ever see one of these, if you ever see the curl is 0, or a vector field has no rotation, you can say that the vector field is conservative. Or if you notice that a vector field has 0 circulation everywhere, that means the vector field is conservative. Or if all line integrals are path independent, that means the vector field is conservative. All of these are basically saying the same thing. Okay? For conservative vector fields. Now the analog to that for source-free vector fields is this. So for source-free vector fields, you have this different requirement. Yeah, there has to be some function psi such that psi x equals negative g and psi y equals f. Unfortunately, there's no notation like the gradient for this, so I'll just leave it in this form. When this happens, the vector field will be path independent. Line integrals will be path independent. You'll have 0 flux, not circulation, but 0 flux. And the divergence will be 0 everywhere. And all of these are equivalent ways of saying the same thing. This is a lot to kind of wrap your mind around. So, you might just want to, hold on to this. You kind of digest as you go. But just one thing to point out is these all say the same thing. And these all say the same thing. If you get one of them, you get the rest for free. Like if you get this one, then you get the other 3 for free. All right. All right, and finally, the last thing I wanted to talk about is just to give you a quick summary of the different ways that you can use line integrals you can use line integrals on curves that are closed and not closed, and basically whether a vector field is conservative or not. So let's go through the circulation type. So there's 2 types of line integrals, right? There's the circulation type, which looks like this, which doesn't have to be closed, right? Usually it's closed, but doesn't have to be. And then there's the flux type. For the circulation type, sometimes we'll use this notation, but in differential form, it looks like this, f dx plus g dy. And for the flux type, it looks like this, f dy minus g dx. Now, I created a kind of a matrix here. So these are the different types of, this is what you can use basically to evaluate line integrals under certain conditions. So let's say that the vector field is conservative. Oh, not conservative, and it's not closed. Well, if it's not conservative and it's not closed, then you need to evaluate the vector field, the line integral directly. Just evaluate it how we learned how to do line integrals. It's pretty straightforward. It's just a direct calculation. Now let's say that the vector field is not conservative, but C is closed. In this case, you could use Green's theorem instead of doing it directly. The circulation is given by the net accumulation of curl everywhere inside the circle C, which is the region R. Now, on the flip side, these are the nice vector fields. Let's say F is conservative. Well, if F is conservative, you don't need to evaluate directly. You can just evaluate at the endpoints. And if C is also closed, there's really no point to do any work here, because by Green's theorem, when you integrate the curl over that region R, the curl is in a conservative vector field is 0. So you're just integrating 0, which is just going to give you a 0 result. Now the analog to this for the flux type of integrals is like so. If F is not source free and C is not closed, you would just evaluate the line integral directly. We did this back in 17.2. However, if it is closed, you can just you can use Green's theorem flux form and just add up all the divergences. Now, if it's source free, these are the well-behaved vector fields. In this case, you could just use the fundamental theorem for line integrals and just evaluate at the endpoints. And if it's also closed, well, if the divergence is 0, you're integrating the 0 function, and you'll just get a 0 out. Okay. All right. So Green's theorem, fundamental theorem, Green's theorem, the circulation form and flux form, these are extensions of the fundamental theorem of calculus part 2. It turns out that we have 2 more extensions to discuss, and these are in 3 dimensions. So it's a little harder than what we just shown you, but it's doable as long as you can get this down pretty good. All right. When we move to the third dimension, the integration is going to occur over regions in R3. Okay, we don't have the tools yet to like understand Stokes theorem or the divergence theorem. We're going to develop the tools in 17.5 and 17.6. Okay, so in 17.5, we're going to take divergence and curl, which we've talked about in R2. We're going to extend these concepts up to R3. And then in 17.6, we're going to talk about what it means to integrate over a surface, like the surface of the Earth. So we've integrated over, 3-dimensional regions, the solid, but we've never integrated over a surface. So let me stop the video here.